Good afternoon, everyone. I would like to welcome you to our thematic session on dynamical systems at the ICMP this year.
Okay, so we can go to the second speaker of this session. That is Frédéric Faure from the Institut Fourier in Grenoble. Faure got his PhD in physics, actually, working in semi-classical limit in quantum mechanics. And after that, he has been working in quantum chaos and other issues related to classical mechanics. But at a certain point, he saw the light and started to work in dynamical systems more properly. And he has been very influential in applying micro-local analysis technique coming from semi-classical limit and stuff like that, to the study of statistical property in dynamical systems. And that is kind of connected, although it's a different twist to what we heard this morning in Viviane Baladi lecture. So I hand it over to Frédéric, and as you can see, his talk is about does quantum dynamics emerge from a classical chaotic dynamics. Okay. Thanks.
Hello. Thank you very much, Carangelo. So I'm sorry to be on live today. And so in this talk, I would like to present some work done with Masato Tsuji from Kyushu University. The title of this talk is Band Structure of the Ruelle Spectrum of Anosov Geodesic Flows. But we will start with a subtitle that in fact is a question. Does quantum mechanics emerges from classical chaotic dynamics? And this work is based on a recent paper that you can find on arXiv here. The PDF file of this talk is also available on my webpage. And of course, I would like to thank all the organizers of this conference. So I switch. So in the first part of this talk, I will try to explain the meaning and then the motivation of the following question. Does quantum behavior naturally emerges in an Anosov geodesic flow on a compact Riemannian manifold N? Recall that Anosov geodesic flow is well known as a deterministic and chaotic dynamical model. So first, we recall that the geodesic flow is the Hamiltonian dynamics of a free particle that moves with unit velocity on the manifold N. In fact, the dynamics takes place on the unit cotangent bundle of N that we have drawn here. The sphere of directions of the unit velocity is represented here by a vertical dashed line. In the unit cotangent bundle that we call M in this talk, the flow is generated by a vector field X, defined from a Hamiltonian function that is simply the norm of the momentum vector P. If the manifold has negative curvature, then the geodesic flow is Anosov. It means that each trajectory is unstable with a transversally unstable direction, EU, and a stable direction, ES. As a consequence, although the dynamics is deterministic, it looks like chaotic, unpredictable, and confusing. On this picture here, you can observe that if you put a tiny adhesive strip on a base starting from a given point and a given direction, then it will follow the corresponding unique geodesic. And in a zone with negative curvature, as we have here, you can also observe that the sensitivity of trajectory with initial conditions, with respect to initial conditions. On this picture, you can observe that on a smooth surface with flat parts, if the size epsilon of the part that has negative curvature goes to 0, then the dynamics of the geodesics is similar to the dynamics of a particle in a dispersive billiard with reflections on the boundary. We recall the talk of Viviane Baladi this morning. She explained the dynamics in dispersive billiards. And the negative curvature, in fact, is concentrated on the convex boundaries, where the reflection takes place. On this picture, if we start at time 0 with a smooth distribution on phase space, so phase space means the unit rotation bundle, and if this distribution has initially a very small support, then we look at this distribution transported by the geodesic dynamics in the billiard. And we observe that due to dispersive reflection on the boundaries, the distribution spreads very rapidly over the surface, and for a long time, it seems to converge to a uniform distribution over the phase space, called equilibrium state. Here we can see some videos. Maybe I can show you. You see? So this is a single particle. It looks like random, but this is deterministic. And here, this is not a single point, but this is a smooth distribution that evolves in the Sinai billiard. And after few reflections, it takes a microscopic size, and after it spreads all over the billiard. And after a long time, you see, so what you see is the projection of the unstable horocycle manifold. And after a long time, it converges to the equilibrium state. I come back, sorry. Here, the colors correspond to different directions of the velocity. And mathematically, this convergence to equilibrium state is in the weak sense of distributions and is called the mixing property of the dynamics. In fact, later, we will not be interested so much with the equilibrium state, but we will be interested by some small fluctuations around this equilibrium state. Now, let us explain the words quantum behavior that appear in the initial question. For this, there is a correspondence between classical Hamiltonian function and operators called quantization.
The second law of thermodynamics tells us that everything in the universe tends towards disorder, and in complex.
Sorry. So there is a correspondence. For example, to the component Pg of a momentum vector, we associate the operator of partial derivative with respect to the space variable Qg. Then, for the Hamiltonian of a geodesic flow, namely the norm of P, we get the so-called wave operator, that is the square root of the Hodge Laplacian operator. This wave operator is the generator of the evolution equation for a function ut on the manifold n. And this gives the famous wave equation on the manifold. In summary, the wave equation on n is the quantum dynamics that corresponds to the geodesic flow. In some classical analyses, there are some important theorems, so-called WKB theory and Egorov theorems and others. They show that in the limit of small wavelength, the solution ut of the wave equation is approximately transported by the geodesic flow, as somehow this figure shows. In physics, the manifestation of this property is that geometrical optics with rays, that is Hamiltonian dynamics, in fact, is a good approximation of wave optics because the wavelength of light is around micrometer, so very small at a human scale. Similarly, the classical mechanics of Newton or Hamilton is a good approximation of the quantum wave mechanics of Schredinger. However, this is important to observe that our initial question concerns the opposite direction. Does the wave equation appears as an approximation of a geodesic flow and not that what we have explained from semi-classical analysis? So let us first discuss some indications for this, and even before, we will present the geodesic flow from different points of view, namely functional analysis. We have seen that the dynamics of the geodesic flow is the evolution of points or particles on the cotangent space, but it defines also a natural evolution of functions by pullback by the flow. The generator is the vector field X itself, seen as a derivation operator. Let us observe that the L2 adjoint of a pullback operator, called Ruelle transfer operator, is a push-forward operator that transports probability densities under the flow. For example, the action on a Dirac measure at some point M is the Dirac measure at the point tip M as the evolution of points or particles. And considering the vector field as an operator is a very fruitful point of view because the important questions of understanding long-time behavior of the dynamics correspond to questions about the spectrum, eigenvalues, and eigenfunctions of this operator. And these objects are invariant objects by the dynamics. And there have been a lot of progress along this direction these last years, from the important work of David Ruelle to more recent work of young mathematicians. In particular, the theorem of Butterley and Liverani shows that an Anosov vector field X, or more generally an axiom A flow, has an intrinsic discrete spectrum in some adequate anisotropic subwave space. That is not the L2 space, but contains smooth functions. This discrete spectrum is called the Ruelle spectrum of the vector field X. However, the discrete spectrum of the vector field X is not obvious at all in general. There is only one obvious eigenvalue, that is 0, for the eigenfunction that is a constant function, just because X is a derivation. For simple models, the Ruelle spectrum can be computed. For example, for a contracting linear vector field on R, where the origin is a fixed point, we check that the eigenfunctions are the monomials x power k, and the corresponding eigenvalues are the negative integers minus k. Let us consider another very special model, the geodesic flow on a compact surface with constant negative curvature. This can be modeled using group theory, namely here the unit cotangent bundle or phase space is the three-dimensional SL2R group quotiented by a discrete compact subgroup gamma. And using representation theory of SL2R, we obtain an explicit description of the discrete Ruelle spectrum of the geodesic vector field X. This is this picture. This corresponds to some work of Selberg in the 50s, also Marina Ratner and Flaminio Forni, and more recently, a contribution by Dyatlov, Guillermo, and myself. From the so-called principal series of SL2R, the Ruelle spectrum are eigenvalues that belongs to vertical lines. The real part is at minus 1/2, minus 3/2, minus 5/2, etc. So minus 1/2, minus integer k. And the imaginary part of the eigenvalues is the square root of μl minus 1/4, where μ0, μ1, μ2, etc. are eigenvalues of the Laplacian operator on the compact surface N. Here, the Laplacian operator appears because this is the Casimir operator of the group. So a very special operator that commutes with every vector field in the Lie algebra. So, on each vertical line, we see the appearance of the wave operator, namely the square root of the Laplacian. There are other discrete real eigenvalues in this picture. They are on the real axis, on negative integers. To understand the meaning of the Ruelle spectrum from a dynamical point of view, let us observe that if x has an eigenvalue a plus I omega, then the pullback operator exponential tx has an eigenvalue that is exponential et times exponential I t omega, where the real part A gives some exponential damping if it is negative, and the imaginary part omega gives some oscillations. In conclusion, up to a finite number of eigenvalues that may be dominant here, as the equilibrium state at 0, the long-time behavior of a geodesic flow is governed by these eigenvalues on these lines, and so is governed by the effective operator on the first few vertical lines, namely the wave operator with some exponential damping in front. If we want to understand the long-time evolution of a smooth probability distribution under the Anosov geodesic flow, this would describe some exponentially small fluctuations above the equilibrium state, and these fluctuations would be described by the wave equation, namely the corresponding quantum dynamics. So this is what we can guess from this spectral picture. We have therefore observed an indication for the emergence of quantum dynamics from the geodesic flow of a particle. One may wonder if this is an exceptional algebraic phenomena, or if it can be present also for a more general Anosov geodesic flow, namely on a Riemannian manifold with non-constant negative curvature. To present our results, we first need to present some effective classical dynamics that will appear later, and corresponding vertical bands. From now on, we consider a general Anosov geodesic vector field X on a manifold M, that is the unit cotangent bundle of N. And let K be a positive integer. For every point on the manifold M, let us consider ES, that is the stable direction of the dynamics. This is a linear subspace of a tangent space. Then, all K of ES is the vector space of homogeneous polynomials of degree K on ES. We take the tensor product with the one-dimensional space of the dual of half densities on ES. And this gives a vector space that we call Fk. Globally, this gives a vector bundle Fk over the manifold M. And sections of this vector bundle Fk evolve under the geodesic flow, and we will call XFK the generator of this evolution. Then, the spectrum of the operator XFK in the L2 space of sections is contained in a vertical band here, whose real part is the interval gamma k minus, gamma k plus, with gamma k minus or plus defined explicitly from these expressions in terms of the dynamics. For example, in the case of a surface with constant negative curvature, because the Lyapunov exponent is constant and equal to -1, then, from this definition, we can deduce that gamma k plus or minus is equal to -1/2 minus k. So, for that case, vertical bands are the vertical lines that we have seen before. Yeah. But in general, we have only these estimates for the values of gamma k minus and gamma k plus. Some estimate in terms of the maximal and minimal Lyapunov exponent of the dynamics. In particular, we see that if k is large, because lambda mean is negative, then the band goes far on the left of the spectral domain. However, these bands can overlap if the Lyapunov exponents are very different. Now, we present the main result of this talk. This concerns an Anosov geodesic vector field X, or more generally, a contact Anosov vector field on a contact manifold N. For any integer big A, that is the number of bands that we consider, there exists an anisotropic Sobolev space H omega, such that for any positive time t, we can choose parameters sigma 1, sigma 2, large, and this is explained later. We can choose a large cutoff frequency omega, and we obtain the following equation. The pullback operator by the geodesic flow, exponential Tx, is equal to the sum of quantum evolution operators over the first k plus 1 bands, plus some finite rank contribution that contains, for example, the equilibrium state, and a correction that is small in operator norm if t is large and if k is large also, just because gamma k goes to -infinity. So this theorem shows indeed that for a long time, some quantum behavior emerges from the classical dynamics of the Anosov geodesic flow up to some finite rank effects. We discuss now some direct consequences of this previous theorem. First, we have seen that the L2 spectrum of the generators XFK, called symbols, are contained in vertical bands. As a consequence, due to quantization, the discrete Ruelle spectrum of the vector field X is also contained in the same vertical bands up to some corrections that are small in the high frequency limit. That is called the semi-classical limit. So the high frequency limit is when omega, that is imaginary part of Z in the spectral domain, goes to infinity. So we do not control what happens when omega is small here. The finite rank operator R omega of the previous theorem may also give a finite number of Ruelle eigenvalues at low frequencies, in particular the equilibrium state at 0. moreover, in each band, the Ruelle spectrum is discrete, and we get an asymptotics for the density when omega becomes large. This is called the Ruelle law. Observe that the density grows like omega power d with a precise prefactor. This comes from the measure of a symplectic volume for the corresponding effective classical dynamics. Similar band structure has been observed in different models. For example, Semyon-Dyatlov get a band structure and Ruelle law for a regular normally hyperbolic trap set, a model that is used to describe waves around a black hole. Michalo Procesi and Colin Guillermo have also obtained a description of the first band for the Ruelle spectrum of a contact Anosov flow in dimension 3 using horocycle operators. The proof of the previous theorem relies on the use of semi-classical analysis for the pullback operator exponential Tx. An important ingredient is the use of a metric on the cotangent bundle that is compatible with the symplectic structure and adapt to the dynamics. From this metric, we defined a wave packet transform, or called FBI transform, that allows to do the analysis on the cotangent bundle T star M. In fact, this wave packet transform is a kind of local Fourier transform. This metric measures the size of wave packets and somehow the uncertainty principle. We can give more details about the proof. The flow takes place on the manifold M, and here you have the Anosov hyperbolic structure of the dynamics, but it is natural in microlocal analysis to consider the lift flow on the cotangent bundle T star M. Since the flow is Anosov and contact, it preserves the Liouville one form A, that is a contact one form. This invariant one form defines the symplectic submanifold sigma of T star M, shown in green here, and transversally, the dynamics of the lift flow is hyperbolic. Consequently, sigma is the so-called trap set or non-rendering set of the dynamics on T star M. Then, using some specific weight on T star M, we can neglect the outside of a trap set. This gives the anisotropic Sobolev norm that we have to work with. Now we can work only with the trap set, sigma, or more precisely with a large vicinity of size sigma. Then, if you consider any point ρ on the trap set sigma, then the tangent space T ρ of T star M is decomposed naturally into the sum of the tangent direction to sigma, here, tangent to the trap set, plus the normal direction to sigma, n ρ, that is shown in red here. As usual, the passage from T star M to the base manifold M is expressed as a quantization. The result of this analysis is that there is a contribution from the tangent direction to sigma that gives the internal quantum dynamics inside each band, and a contribution from the normal direction n that gives the band structure with index k. For this last part, recall the simple one-dimensional model of a fixed point where the monomials are eigenfunctions. More generally, here, this is replaced by the homogeneous polynomials of degree k. In conclusion of this talk, we have considered the internal structure of the Ruelle spectrum of an Anosov geodesic flow beyond the equilibrium state. And on this last slide, here is some unrelated observation of the surface of the sea, but we may find some similarities. And thank you very much for your attention.
So there is some question. Yes?
Thank you for your talk, Frédéric. This was very mathematical. If you would tell us, as a physicist, what it means that you have quantum behavior coming out of chaotic behavior, how would you formulate it?
I will say that suppose you observe, as I shown, a probability, a cloud of points in the billiards, okay, or probability distribution that evolves under the dynamics. Then, from a first look, you see that the probability distribution converges to the uniform distribution, okay, so to a constant. But now, if you subtract this constant, okay, you will observe the fluctuations around this equilibrium state. And these fluctuations, the result is that these fluctuations are controlled by the wave equation. So this is maybe this is still too much mathematics.
No. Thank you.
Okay.
Some other question? If not, maybe I ask a quick question. In the case of constant curvature, you showed that the Ruelle resonances are related to the Laplacian. So I wonder, is there any possibility that in the non-constant case they are related to some other second-order operator, some Laplace-Bertrami operator, or some version thereof?
Yes, so yes, we can compute what is called the principal symbol of the operator in general, and so indeed it has the same principal symbol as the Laplacian, so the square root of the Laplacian. But in general, we do not expect that it is exactly equal to a Laplacian, usual Laplacian. But as a first order, yes, it's similar.
Okay, so if there is no...
Yeah, I have a quick question, sorry.
Yep.
I heard a talk by Anke Pohl not long ago about resonance states on Schottky surfaces, and I see a number of striking similarities to your band structures, but this is just, so to say, from comparing these two talks from memory. Are you aware of any connections that are systematic? I mean, the band structures there are much more complicated, of course, but I thought it was quite striking.
Yes. So the dynamics on Schottky surface is axiom A. This is not Anosov, and so, but it is a geodesic flow, so it is a contact dynamics. So our result does not apply to axiom A flow, but of course, as I said, we know that Ruelle spectrum is discrete also for Schottky surface, and I don't know if there are some exact band structure for Schottky surface, but I expect, but they are not bound from the left, I think.
I think much of it is still largely conjectural and based on extensive numerics, which is complicated enough there, yeah? But yeah. Thank you.
Okay. Fine. So maybe we thank the speaker again. And Frédéric, you should receive, you went away. Okay, you will see it eventually. All right. So maybe we are running a little bit late, so we start immediately with the next talk. That will be from Michela Procesi, and she got from Rome 3, and actually she got her PhD also from Rome 3, although in the intervening time she has spent some time in Naples. And she graduated with work on Arnold diffusion, but she has been working also in asymptotic integrability. She has a super cited book on that. And lately she has been focusing on periodic and quasi-periodic solution for PDE, something like nonlinear Schredinger, wave equation, and so on. And of course, as usual, I forget the title, but here she is. And since you are here in person, you even get the medal immediately. So this is yours.
So how am I supposed to?
I do not know. You should have there.
Yeah, but come cambio?
And this is the object. You should be able to.
And should
you
I
can
do
look at
some?
it here.
Sì, ma. Okay, that's
Yes,
perfect.
and you should be able to move.
Yes.
And there should
And
be also
here's-
a pointer if I think.
And the pointer. Wonderful.
Okay.
Okay, so
Can you remove the mask, please?
Yes, now you can.
right, I remove my mask. So I'm really happy to be here in person. I didn't believe it, so I actually forgot to erase that we are not in the other, but I'm actually in person. So I'm happy to be here. Well, this talk is not actually on my.
Try to be close to the
Così?
mic.
I'll try. Is it really necessary? It's okay. I will try. I cannot see what I'm. Okay. So this is not really my area of expertise. It's joint work with Laurent Stolovic, and I think it's a really nice problem which connects algebraic questions with questions coming more of dynamics. So it's the problem of linearization of a dynamical system. So let's see if I can manage like this. So the question is the simplest as possible if I put it in a naive way. I take a dynamical system with a fixed point at 0 in finite or infinite dimension. Obviously, I will be interested in the infinite dimensional case. Otherwise, this is a very classical problem known since mid of the 20th century. Sorry. So can I conjugate my dynamical system to a linear one? And just to set up notations, of course, I will have to be much more precise if I want to work in infinite dimensions. But my point is, take my linear system, L is a linear operator, N is a nonlinearity, and since, let me say, I will always consider extremely regular questions, so I will assume that N is analytic. So I'm just saying that the Taylor series starts at least at degree 2. And then I am asking, is there a change of variables, which I think, I called phi, I called it psi here, sorry, which conjugates exactly to the linear system, exactly the same linear part where I started from. And in finite dimension, this is an extremely classical question. And what my point will be is give you the finite dimensional questions and then try to see what goes on to infinite dimension and in which context. Okay, so first let me run you through the finite dimensional case. Sorry, no, I forgot. This is just one of the simplest possible questions in the more general class of questions of normal form. So you might ask yourself, I take my dynamical system, then I have a group of changes of variables, and we have to specify which group I want to consider. And I wonder if this if my dynamical system can be conjugated to some particularly nice form. Possibly, I might want to send it to its linear part plus a correction which might be explicitly integrable. Or maybe in infinite dimensional systems have some nice properties like preserve the Sobolev norms or do whatever you might want to do. And of course, this depends on which system you're looking at. And if you think at the finite dimensional case, it depends on basic things like, are you on the reals, are you on the complexes? I did not say at this point. Is my system Hamiltonian? More refined, is L semi-simple? Does it have distinct eigenvalues, so it's regular semi-simple? Is it maybe imaginary spectrum, mixed spectrum? So these are all questions which one has to cover. And also, of course, it depends on what kind of, I really cannot point and speak like this, it's impossible, sorry. Non so come fare. Sì, ma no, se voglio far vedere un punto devo puntare. Well, okay, I'll manage. Sorry for the Italian. So, I was saying it depends on the regularity of the change of variables that you consider, of course. And what I am going to do, as for the first question, I am going to consider a Hamiltonian system. I am going to assume that it has an elliptic fixed point, so my linearization problem will have small divisors. And then I will assume, as I said before, that n is an analytic function. N is the nonlinear part of the vector field. So if you think of a PDE, this thing that n has to be an analytic function, that's not such a weightless thing to ask. It's many interesting PDEs do not have this property, and I will show you my point afterwards. But I really need this to, up to now, to give my results, so consider it. And the other point is I have two interesting questions. Probably there are many, but for me, if the vector field is analytic, you have 2 points which are interesting. One, group of change of coordinates which is analytic, and see what happens there. And the other is at a purely algebraic level. Of course, you have formal power series, at least in finite dimension, this is completely clear. It was the first things that people did. So you have formal power series, you have formal changes of variables, and you want to see what happens there. And so these are the two kind of things that you have to consider. And so this was known, I think, by Poincaré and Birkhoff, who started doing these things. So the first results are without small divisors, which is when the eigenvalues are in this so-called Poincaré domain, which means that, and in that case, which will not be my case, alas, if you have that your dynamical system can be linearized by a formal change of variables, then automatically, at least in some ball close to zero, remember your dynamical system has a fixed point at zero. So at least in some ball close to zero, it can be linearized by an analytic change of variable. But the point is that if you are, in my case, so Hamiltonian system with an elliptic fixed point, this does not hold. You have small divisors, and this is a well-known fact. So formal linearization does not mean analytic linearization. And this was, in fact, the beginning of KM theory. And so the first result, Siegel, and then Russman, Bruno, and they all produced some conditions that you have to ask on the linear part in order to achieve this linearization theorem and normal form. So this is my context, and I will show you first in the finite dimensional case because it is simple and because really my idea, well, the idea when we started talking about this with Laurent was to keep it as close as possible to the finite dimensional case and see what goes wrong. So Notations, I have a finite dimensional Hamiltonian system. This is, in the vector field, this is the linear part, so this is the quadratic part of the Hamiltonian, which you see, I never wrote it, but omega are real numbers. So this is an elliptic fixed point with frequency omega. And then I have a nonlinearity, so this piece here in the Hamiltonian has minimal degree 3. And I'm really the simplest possible case, so I have the usual standard symplectic form. And what is nice and what I want to do, because it's closer to my PDE setting, is to pass to complex notation. So complex notation just means that I'm taking a complex vector u, and p and q are the real and imaginary part. And when you apply this, which is a symplectic change of variables, you get the Hamiltonian with the nonlinearity, and then the dynamical system associated in these variables is written like this. Okay? Nothing particularly interesting. Remember that since I am starting with a real Hamiltonian, when I say that P is analytic, it is real analytic, which means that you have a Taylor series of the form which I might be able to point. Okay, so real analytic means this Taylor series convergent in some ball close to 0. And since I'm in finite dimension, I don't have to give any functional setting, but when I will pass to infinite dimensions, these things will become very important. And then, what does Birkhoff normal form say? Well, it says, assume that omega has rationally independent entries. Just the omega j's are independent over the rationals. And then, for any k larger or equal than 0, you have an analytic change of variables generated by a polynomial, such that something is wrong. Yeah. So the Hamiltonian is conjugated, you see, to the quadratic terms plus this piece here, which depends only on the actions in such a way which I don't know, but this is surely integral, plus a remainder. And what is the interesting thing about the remainder? It says it's analytic, and it has a minimal degree 2k plus 3. So something that goes to infinity while k goes to infinity. And it's perfectly well known that this is not a convergent procedure in k, but if you go at the level of formal power series, this converges. And then you have a change of variable, which of course is just formal, which conjugates to linear part plus something which is just function of the actions. And Z is unique. So this is what we wanted to reproduce in infinite dimension. Exactly this result. So, sorry, a bit more quantitative, because this will be an important point. Assume some Diophantine condition. These are not the weakest conditions that you can assume to have results of this type. They are the so-called Bruno conditions, but I'm going to stick to simple things. So assume that you have not only the omega j's are irrational, but they are rationally independent, but you can bound from below the linear combinations with integer coefficients. Then you can be quantitative, and you can say that the Birkhoff normal form gives you a stability result, in the sense that if you start in a little, with the initial datum in a little ball around 0, then the solution of the Hamiltonian flow stays in a slightly bigger ball for a very long time. And how long the time is depends on k. Of course, I am not saying there are some constants which depend on k, both in front of the time and in front of the smallness conditions. But this is the kind of result that you... And the second, so you could compute everything, choose k in order to maximize the time, and that's the Khorashev type result or stability result that I have in mind. And the second question is what I told you at the beginning, a linearization theorem. So start with an analytic dynamical system, assume that the formal Birkhoff normal form satisfies that z is equal to 0. Remember, it's unique, so this is a well-posed question. Then you can prove that the change of variable which linearizes it is in fact analytic in a ball around 0. Okay? So now I really said what kind of results I want to. So let's go to infinite dimension, and I guess I have to go a little bit faster, otherwise we'll never reach there. So in infinite dimension, I'm considering the simplest possible case, which means that if you remember, in my finite dimensional case, here I had a finite sum, so I'm just going to consider an infinite sum. And then P is a function of these infinite variables uj. So this could be, you can think of it as a chain of harmonic oscillators, each with frequency omega j, coupled by a nonlinearity. So you have a symplectic structure, you have everything you like, and this makes perfect sense from a PDE point of view, except that if you're working with a PDE, which is actually what I want, you have to think that the Hamiltonian will not be defined on the whole L2, but it will be defined on some smaller space, let's say H1, or well, you have to ask more regularity. Other point is, typically the vector field will not be bounded. You will have derivatives in the nonlinearity, in the linear term, so this has to be taken into account. Also, a basic point in Birkhoff normal form is that polynomials are analytic in finite dimension, but in infinite dimension, this is not true. So this will come into play. And topologies are not all the same, so when I say I take a small ball around 0, well, it depends in which norm. So these are all rather naive points, but they have to be the important things. Ooh, I was breaking my medal. So here is my model. Well, this is just the Hamiltonian. What are the conditions? So my first condition, this comes from the fact that I'm thinking about a PDE, and also technically I need it. So the frequencies will go to infinity as j goes to infinity. And I'm asking j squared, not because I couldn't do j to the cube or j to any power greater than 1, but because this is the nonlinear Schredinger equation. And so I like this. Second condition, this is debatable. I could weaken this, but I put it. I want some constant of motions, and I want them to be pretty simple. So two constants of motions which are natural for the NLS are mass and momentum. And so I will ask that I have these two quantities preserved. And then the third question, this is a bit subtle. So I want that not only P is an analytic function, but I want P is the nonlinearity in the Hamiltonian, but I will want that when I compute the Hamiltonian vector field and I compute its Cauchy majorant, whose definition I've written below, it's just pass through the Taylor series and take the absolute values of the coefficients. I want that the Hamiltonian vector field of this thing here has to be an analytic function from a small ball in H1, it's written there, to H1. H1 is the usual Sobolev space, one derivative in L2. Okay? So this is a pretty heavy condition, but I really need it. Even just removing the fact that it's the Cauchy majorant, it's a big deal. So, and the questions, what I said before, can I perform a Birkhoff normal form? By Birkhoff normal form, if there are people in PDEs, I mean in the finite dimensional sense. So I really want to reduce to something which is, depends only on the actions, plus something which is a high degree polynomial. And do formal Birkhoff normal, do formal power series make sense? And does the linearization theorem hold? These are my questions. And the answer is yes, if you give good Diophantine conditions and if you work on good scales of Hilbert spaces. When do I have to stop? Perché ma ho iniziato 10 minuti dopo. So, yeah, and I'll keep speaking. So, as I said, but maybe I will skip this, a good example which fits all my hypotheses is the nonlinear Schredinger equation. And this is mostly why I use the hypothesis. So, maybe, well, to have an idea what the spaces were, we thought that we should look at results of stability, because Birkhoff normal form gives stability for PDEs, exactly for the NLS equation. And it turned out results were mostly in this class of spaces, which seems a bit daunting, but it's not a big deal. You see, you have that the Fourier coefficients should decay, and if you have this parameter A positive, this means that they decay exponentially, so you have an analytic function. If you have the parameter S different from 0, and A equal to 0, then they are in a Gevrey class. And if S and A are 0, and you just have P, then you are in Sobolev class, okay? So all the results were here. And all the results gave exactly what one expected. Start in a small ball in the Sobolev space, and then you stay in a slightly larger ball for some time computed explicitly. So this was the context we wanted to look for, except, unfortunately, they didn't really do Birkhoff normal form, or fortunately, otherwise this would be a much shorter talk. So their point is that they had rather bad Diophantine conditions. So with Luca Biasco and Jessica Massetti, we decided, we were looking around on these things, and we came on a condition given by Bourgain in the context of almost periodic solutions for an LS equation. And this Diophantine condition, well, it looked very nice. Maybe I'm not going to comment too much, otherwise my 10 minutes will finish. But it's much simpler than all the ones that were written in previous papers, and very clean. And if you look at it and think of a finite dimensional system, then it gets, you see it, it's here. It's very close to what you would expect of a Diophantine condition in finite dimension. And others did not satisfy these conditions. And then, well, what we do, we just decided to try this condition and see what stability result we got. And so we got many stability results. They're on a paper on CMP, but this is the one I'm going to concentrate on. So I ask that the frequencies are Diophantine. Then I assume that my sequence is Gevrey. So I'm asking, remember, S gave the sub-exponential decay. This has to be positives. And then I assume the condition that I wrote before, so that the nonlinearity is normally analytic from H1 to H1, okay? Then what you can prove is that you can construct an invertible analytic symplectic change of variable, but this does not map H1 in H1. It maps a very much smaller space into itself. And this space, HPSA, remember, S is positive, so this is strictly smaller. Okay, and under this condition, the map that you get has that Z depends only on the actions, and R is, is an analytic function with minimal degree 2k plus 4. Well, this plus 4 instead of 3 is just because it has to be even. And so that was exactly what we were looking for, with good bounds. Then you can ask yourself, can I go to the formal power series level? Well, the answer is, of course, you can do formal power series in infinite dimension. Only you have to remember that polynomials are formal power series, and you have to be a little bit careful with what you do. You can give it a symplectic structure. The problem is that it's not closed with respect to Poisson brackets. And this is a fact. I mean, you can produce examples. So what do you do? Well, it's rather simple. Remember I told you constants of motion. Well, the fact is that if you just look at formal Hamiltonians, which formally preserve momentum, which is a condition on the monomials, then everything is perfect, and you get a a natural filtered Lie algebra structure, which means, in words, that it's closed with respect to Poisson bracket. You have the definition of homogeneous polynomials, even if they are formal, and Poisson bracket of homogeneous terms are still homogeneous. And well, I just rescaled the definition of homogeneous if you are surprised why there is not a -2 in the slide. But so this, the last thing that I wrote is the only thing that was a little bit harder to prove is that you have a group of formal changes of variables, which you can give just by the exponential of the Poisson bracket, exactly as in finite dimension. This is Baker-Campbell-Hausdorff formula with a little bit of hard work on it. But the rest is, goes, once you had the idea, which was given by Theola, Giuliani, and Pasquali, you just go. And then what you have exactly everything that you would expect in finite dimension. So you have the normal form. The normal form is unique. And the other thing is assume that you're starting with an analytic nonlinearity and assume that the system is formally linearizable. Then there exists analytic change of variables, which puts you to, which conjugates exactly to the linear term. And before I stop, let me go to this slide, which I think is interesting. So I didn't even attempt to give you the technical parts because they're really unpleasantly technical. But the interesting thing, which I think was a new paradigm in some sense of, it was Bourgain's idea actually, but we thought about it a lot and we managed to use it here. So the point is, what you have to do, you have to assume that your vector field is bounded on some rather large space, let's say H1. And then what you are going to do is you're going to ask that your change of variable is bounded on a much smaller ball, but not typically in Birkhoff normal form, you say it's a smaller ball because you just take the radius smaller. But here the idea is that you have another parameter, which is the regularity. And so, but the important thing is, of course, oops, what did I do? Of course, a small ball in a more regular space is contained in a small ball in a less regular space. The point is that the image is in the same regular space. So it's from the phase space to itself. And that requires some rather heavy analysis, which you can find. I forgot to say it, this paper with Laurent is on Archive. It appeared, I think, today. So if you're curious, you can look at it. And the points are really show that when you restrict the domain by getting higher regularity, you also get in the same phase space. And then after that, if you know Birkhoff normal form, you have to do exactly the same things. So I think my time is up, and there is some place somewhere to say thanks, but it's thanks.